Okay, here's our topic. Thermodynamic favorability is a new one. All right, here's our objective. What it means is we want to know this value for a reaction. We're going to calculate it. All right. Another way to think of it, another facet of calculating it is once we get the value, is we're going to understand what it means. And I will add a little bit more about what this, in terms of what it means in terms of thermodynamic favorability. So I love the poem Desiderata, which is actually uh, desired for in Latin, particularly this last line. This isn't all the entire poem, but this line here. And whether or not it is clear to you, no doubt the universe is unfolding as it should. The universe has a plan, all right? And thermodynamics, in some ways, helps explain the universe's plan in terms of science. And that's why I want to use this expression. The universe wants it to happen. Typically, things that are thermodynamically favored tend to happen. They tend to happen on their own a lot of times because these two things happen. Matter likes to be stable and matter doesn't like to have lots of energy. So it reacts to lose energy and to become stable. This is changes in enthalpy. Also, it tends to act in a way to mix and randomize and microstates, more entropy. Keep in mind, however, this term thermodynamically favored or favorable does not mean fast or slow. It could be a fast reaction and it could be a slow reaction. All right? So Gibbs Free Energy, it measures whether or not something is thermodynamically favorable. Its symbol is delta G. Like enthalpy and entropy, they can be positive or negative values. Negative means it's thermodynamically favored, and if it's positive, it's not. All right. Now, how would I calculate it? You'd calculate it the same way as you would calculate uh, entropy and enthalpy for standard state, in that you look up your enthalpy of your Gibbs free energy of formation, and you subtract the sum of the products from the sum of the reactants. All right, here we go. That's just the standard state: 1 atmosphere, 1 atm, 1 molar. Here's another way to think of what that means. Wow, these, like enthalpy, these delta G's of formation are going to be zero for elements in their standard state. This is oxygen gas, graphite, for carbon, sodium metal, all right? But not like entropy. Entropies, those values are not zero, all right? The steps to fill this in or to calculate it is the same as it was for enthalpy and entropy. Steps are the same. Here they are. All right. Now, here's a problem. Here's our problem. All right. Give you a chance to read it. The first thing we'd need to know is we'd need to know a balanced chemical equation. All right. And I'm going to have ozone is going to be a product. I'm going to have a hydrocarbon. It doesn't specify. I'm going to give it to you. But oxidation is reacting with oxygen here. So typically when hydrocarbons react to make oxygen, they make water and carbon dioxide. All right. Here we go. There it is, the balanced equation. Now, the next thing I would do is I'd look up my standard Gibbs free energy formations. Here they are. All right. And then what I would do is I'd plug them into this formula, keeping in mind I'm going to multiply each value. So 2 times 50 is going to go right here for the reactants. All right. When I plug it in, that's what it's going to look like. It's a big problem. All right. And I'd simplify it, write it down, and that's what I get. Now, this is a huge amount of energy. That means um, if this were to happen, it would release a lot of energy into the atmosphere, and it would also release ozone, which is not good. All right, but that's how you would do it. All right.